Okay, well, thanks very much for inviting me to give this talk. I'd like to talk a bit about one particular system, lanthanum calcium copper oxide. And this work was done by my postdoc, Sajjana Hamid. Really did a wonderful job on this, and the group leader in charge is Matteo Minola. And the lanthanum calcium copper oxide system is special because it allows you to really go to 50% doping. And what these two guys did is to investigate charge order and spin excitations using resonant X-ray scattering. And so the question that underlies this work is the influence of disorder, which was already discussed several times at this workshop, on the interplay between these different states, charge order, pseudogap, superconductivity, and in particular, the extent of the superconducting dome, right, that Peter Hirschfeld was discussing. And the overarching question is, well, we're interested in what the phase diagram would look like in the absence of disorder in a hypothetical clean system that is described by a standard many-body Hamiltonian. Okay, and for this particular material system, we were also motivated by this paper here, which claimed that the end of the superconducting dome coincides with the onset of a new charge-ordered phase with an unconventional wave vector, 1/6 the Brillouin zone. So the question then is, is perhaps the onset of charge order responsible for the disappearance of superconductivity rather than disorder? Okay, so lanthanum calcium copper oxide is interesting because just looking at the ionic radii of the different ions here that you can use to substitute lanthanum in the 214 system, calcium is by far the closest to lanthanum. So just from the ionic sizes, there should be minimal lattice disorder compared to strontium and barium. Okay. Now, unfortunately, lanthanum calcium copper oxide is unstable in bulk form. When you try to synthesize it with a calcium level of more than, say, 10%, it disintegrates into two different thermodynamic phases. And what Georg Kim here, also working in our institute, realized a few years ago is that you can actually epitaxially stabilize this material by growing it on an appropriate substrate. Okay, and when he did this, he found that superconductivity is actually stable up to much higher doping levels than in bulk lanthanum strontium copper oxide and also in thin film lanthanum strontium copper oxide, presumably as a consequence of the reduced lattice disorder. Now, of course, it's pretty difficult to assess whether the material is really doped, whether the chemical substitution is really taking place. And we did the very best we could to make sure that this is indeed the case. For instance, we measured the Hall effect. It continuously evolves up to 50%. Optical conductivity also keeps evolving as you keep adding calcium. And some phenomenological analysis of the optical spectrum seems to be in pretty good agreement from what you expect in electronic structure theory, especially a six-band model proposed by Gabi Kotlia and collaborators. So, we can never be perfectly sure that this persistence of superconductivity is not due to some kind of inhomogeneity, but I think we're pretty confident that we haven't made any stupid mistakes here and that, the system is really approximately doped to 50% within some error bar that is difficult to estimate. Anyway, so now what recently happened in the group is that Sajna um, applied the resonant X-ray scattering technique to look for charge order, as this Chinese group did in their lanthanum strontium copper oxide crystals. And she found these peaks here, resonant peaks, over a wide range of doping levels. Basically, at every doping she looked, she found resonant peaks at very low doping level. They followed what is known from bulk 214 systems. So, they're incommensurate and move with doping. But then at about doping level zero point 0.2, just about optimum doping or so, the periodicity locks in to 1/4. So that means 4 unit cell periodicity. Okay, so this is not unheard of. This is data from Seamus Davis's group on bismuth 2212 from STM. And they also found a 4 unit cell period superstructure, over a wide range of doping levels. So this is, and there are other systems in which this kind of lock-in has also been observed. Okay, so now to see, what the origin of this superstructure really is, we also did temperature-dependent measurements. And there's quite a distinct doping evolution here. So at low doping, let's say on the upper panel here, 50%, you see a clear temperature dependence, consistent with what has been seen in prior work. You can even see, although it's not so pronounced here, evidence of competition between charge order and superconductivity, meaning that the charge order peak decreases in amplitude when you cross TC. Okay, so now when you increase the doping level, this temperature dependence gradually goes away, and at the highest doping levels, 30% upwards, the superstructure intensity is more or less temperature independent. And that indicates that it is not actually charge order, which is expected to go away at some reasonable temperature, but rather this is some kind of lattice superstructure. Okay, and to confirm the origin um, um, of this superstructure at high doping levels, we also performed non-resonant X-ray scattering experiments that are sensitive to all electrons, core electrons, valence electrons, etc. And they also saw clear evidence of this superstructure. So that confirms that it's really a lattice superstructure, not charge order. Okay, so at high doping levels, so at moderate doping levels, you see, some intensity remaining and at high temperatures. And then a second component coming in at low temperatures. Okay, but at high doping levels, everything is temperature independent and means only the lattice structure remains. There's no evidence of really the previously reported charge density wave formation. So we only have a lattice superstructure. But then at low doping levels, we have both. We have this lattice superstructure at high temperatures, and that sort of seems to template a charge density wave structure that you then only see in resonant X-ray scattering. You need the resonance to actually visualize this charge order. Okay, and now the question is what is the origin of this lattice superstructure? And well, one thing that we can do in our thin film machine is to just change the oxygen content at which these films are grown. And it turns out, while we see in the read pattern, while the films are grown, we actually see a superstructure that we can change by changing the oxygen content. So this implies that it's really an oxygen superstructure, specifically an oxygen vacancy ordering that we're seeing here. Okay. And we can also see direct evidence of oxygen vacancies by Raman scattering. This is work done again by Gidok Kim some time ago. On the left-hand side, that is published work on lanthanum strontium copper oxide, where you see in the middle plots, graphs here, you see these peaks, pronounced peaks, that are characteristic of oxygen defects. And, by changing the polarization geometry, you can actually find evidence that this is due to apical oxygen vacancies. And on the right-hand side, these are unpublished data on lanthanum calcium copper oxide, where you see a lot of regular phonons, but none of these pronounced defect peaks. So that means that indeed, in the lanthanum calcium system, the prevalence defects is much reduced compared to lanthanum strontium copper oxide. And in some sense, these findings are similar to phenomena that have recently been reported in nickelates. For instance, here, this is work by Carl Schen's group, who also found oxygen superstructures in these infinite layer nickelate phases that are not completely reduced. And they measure the temperature dependence, found that, there's no significant temperature dependence, and concluded that this is really an oxygen superstructure rather than the previously reported charge density phase. So it's parallel to nickelates, and so these findings suggest that there's some interplay between oxygen order and charge order. Okay, so at low temperature, the charge order that already exists, and the oxygen order that is formed at high temperature templates a electronic charge density wave with the same periodicity. Okay, so it forces, well, maybe the charge order, electronic charge order, may very well like to be incommensurate, matching some Fermi surface dimension, but there's some commensurability energy gain that makes it favorable to match the oxygen periodicity. But then, there's a converse effect at high temperatures. At high temperatures, the oxygen are still mobile and they interact somehow, right? So it's and then as you lower the temperatures, these oxygen vacancies freeze in. Okay, and this interaction is also determined by the susceptibility of the electron gas. And this kind of effect has been already known since the 1930s, really, where in these metallic alloys, people saw this concentration waves of the alloy composition that matches the characteristic features in the electronic susceptibility. Okay, so this is sort of the questions that are raised by our work. As far as theory is concerned, I think it would be very interesting to actually calculate the interaction parameters between oxygen defects and so predict how they order based on electronic structure calculations. And these oxygen order phases are not unimportant. They appear in many different perovskites, in the nickelates, cuprates, but many other oxides as well. And experimentally, what we're trying to do now is to change the oxygen ordering pattern and see what influence this modulation of the oxygen order has on the electronic properties. So this is all I wanted to say about charge order. If I have some more time, Andrea, I can also say a bit about spin excitations.
Yeah, you have another 6-7 minutes or so.
Oh, okay, good. Then let me just say something about the experiments, recent experiments on spin excitations in these same systems. Okay, spin excitations, I guess I don't need to convince you that they're important. They're one of the candidates for pairing glue. And, so what we and others have done in these articles is to come up with some phenomenological description of how these experimentally observed paramagnons in the cuprates actually induced superconductivity, calculated TC in the framework of some simple Eliashberg calculations and came up with, reasonable numbers, right? And recently, uh, there were some actually ab initio calculations in nickelates that also came up with reasonable numbers for TC. Anyway, so these are some of the RICS data that Sajina Hamid took on these lanthanum calcium copper oxide films. Two different doping levels, optimal doping and highly overdoped. And so these are along one particular direction in momentum space. You don't see very much difference in these spectra. There's slight difference in dispersion relation, but basically these data are similar as far as the dispersion relation is concerned to magnons in undoped lanthanum copper oxide. Okay, so the dispersion relation is similar, and this is something that we had already seen in other compounds. So this is not really a surprise. What it implies is that, okay, these spin excitations remain present up to high doping as a resource for spin fluctuation mediated pairing. So, these bosons are available for pairing. Whether they're actually responsible for the pairing, of course, still is ultimately an open question. So now, so these data sort of match what we had seen in other systems like YBCO or sort of BISCO systems. Um, and then we did another experiment that was motivated by some theoretical predictions some 10 years ago. So there were two competing views of what happens in resonant inelastic X-ray scattering. One was propagated here by Devereaux and others who concluded from their Monte Carlo calculations, the Hubbard model, that the RICS data, RICS process really visualizes the spin-spin correlation function analogous to inelastic neutron scattering. But then there was another set of papers by Bernhard Keimer's group who suggested that you can actually take a simple non-interacting electron calculation model and also reproduce these data, right? But they actually made an interesting prediction, namely that the character of these RIC spectra is not really Raman-like in the sense that you see collective paramagnon excitations, but rather sort of fluorescence-like characteristic of in a particle hole gas, right? And the evidence would be that the center of the RIC spectrum actually shifts with the photon energy. Okay, so depending on what photon energy you choose, you get a different peak position, just like a fluorescence process. And then we worked together with Yi Lu, who was a student of mine at the time, and he did some more calculations and found that actually both of these features are present, and their spectral weight changes as a function of doping. So at low doping, you see this Raman-like RICS process, and the higher in doping you go, the more fluorescence the spectrum becomes, the more this collective magnon excitation disintegrates into particle hole excitations. And this is an effect that we actually found in two different systems, bismuth 2201 and the thallium-221 system. Okay, so at low doping level, you see Raman-like response, and then as you go higher in doping, the spectrum becomes more and more sort of single particle-like. And this is data that Sajina now took on the lanthanum calcium copper oxide, two different doping levels that show essentially the same effect. Right, so low doping level, you see a peak position that's independent of photon energy. And then at higher doping level, you can actually analyze the data in terms of these two contributions, Raman-like and fluorescence-like, that we also found in the other cuprate systems. Okay, and this is sort of the concluding picture here. On the left-hand side, our old data on bismuth, no, it's thallium here and YBCO that show that this crossover between Raman-like, so collective paramagnon type excitation to more incoherent particle excitations is rather rapid around optimal doping. Okay, and the data on the lanthanum calcium copper oxide are, to within the error, identical to those in the other systems, despite the fact that, superconductivity persists to much higher doping levels. So that suggests in turn that the upper end of the superconducting dome that you see in most cuprates, not in LCCO, is not due to some difference in spin excitations, etc., but rather, as many of the theories suggest, really due to a disorder of some kind. All right, so that I think I'm out of time now. Thanks a lot for listening, and I'm happy to take some questions.
Thank you, Bernhard. Very nice talk. Questions, please.
Yeah, so I have a question. Very nice talk. Yeah, so I was just curious that in the underdose regime, where you see charge order, I mean, near 1A, did you see a sort of a junction quadrats or stripes, or at least the charge part, consistent with that? Or?
Yes, it's basically so we don't see the spins
I know. Maybe you
with
cannot.
Rex,
Yeah,
but the charge part is basically, it's consistent with stripe excitations, right? So we don't have evidence of uniaxiality of these of these charge domains here, right? But there's evidence from other experiments, so it's consistent with stripes. Yes.
I see. Okay, yeah. Thank you.
Other questions? I have a couple of questions. First one is, you were mentioning that you're looking at different oxygen ordering for the, in particular in relation to the charge order. So are you looking perhaps at annealing this sample, post-growth annealing, quenching, and things of that kind? What can you do there?
Yeah, it's not easy to stabilize in the same system different oxygen orders. That's pretty difficult to do. We're trying to do that with some success at selected doping levels. Yeah, but basically by growing these films under different oxygen atmospheres.
That's it.
That's what we do.
And then if you look at a plot like this where you see basically you're saying superconductivity. So the charge order now is really having to do with the ordering of oxygen vacancies, yet superconductivity continues. So how sure can we really be about that doping level really being how you quantify down there? You were showing some optical data. What about X-ray absorption? Or well, of course, ideally maybe photo emission just to look at the volume of a Fermi surface.
Yeah, ideal photo emission would be ideal, of course. But I do understand that doing photo emission on films is challenging. But that would be ideal, of course. Yeah.
X-ray
Okay, so we did
absorption.
what we could do. Well, we did Rutherford backscattering to make sure that calcium really has the right concentration. There's no clustering from X-ray from electron diffraction. And the doping level, well, it's from optical spectroscopy, we can analyze the Drude weight. Seem to be also consistent. But okay, the gold standard would, of course, be photo emission. Absolutely. Yeah.
I was wondering also, and given the challenges, maybe X-ray absorption, then you would also have a chance not only of looking at, in X-ray absorption with doping, but maybe even how far, the spectral weight transfer between lower and upper Hubbard band, continues in the system. That could be interesting.
Yeah.
Any other question, Pencheng? Were you about
I
to?
have one more question. I was curious that what do you actually mean by oxygen ordering? Because I thought that in the 214 system, oxygen are you saying there's actually oxygen in the interstitial site, or it's really locked in?
Well, at very low doping levels, you can generate oxygen interstitials, but then as you go up in doping, you tend to generate vacancies.
So these are oxygen vacancies on the
Yes.
regular 214 site?
Yes.
I see.
That's what we believe. Yeah.
But that doesn't change the charge carrier concentration?
It should, but it's very difficult to see. It doesn't seem to have a very major effect according to this optical spectral weight analysis. But it surely will have some effect, yeah. But we don't have any quantitative assessment of the magnitude of this effect.
I see. So you do have a complete crystallography of how the oxygen arranged?
No, we don't. These thin films is hard to
Very
do
difficult, right? Yeah, very
crystal
difficult.
structural refinement, especially since they're grown on top of a substrate that has a very similar structure, right? So it's you can't do it refinement. So what we do is we do these Raman scattering experiments. We see these defect modes, and
I see.
from those data we can extract some information about the nature of these defects.
Okay, thank you. Yeah, very nice.
Okay, any other questions from the audience?
Right.
Yeah, then I guess we